Okay, so in this lecture, let's discuss 3D frame matrix analysis. Okay, so a complete 3D frame has a 12 by 12 stiffness matrix, each member. You know? So that's the stiffness matrix of a complete space 3D space frame. No, so for example, this member here. So if we draw its cross section and its extrusion, you have something like that. So remember, this is the global Z. I make this global G, and each member has what we call the local axis. No? So this is the global axis, while the local axis will be this one. So let's say this is Z, this is Y, and the longitudinal axis is X. Okay, so basically this is also the convention in STAAD. Okay, so each node here, so sorry, each node, the beginning node of a space member, space frame, will have 6 degrees of freedom per node. So 6 degrees of freedom. Therefore, you have 6 per node, 6 here, and then the other end is another 6. So 6 plus 6, that will be 12. Okay, so that will be a 12 by 12 stiffness matrix. So what are those six forces? So number one is the fx, say this is our okay. But before that, let me check on the stiffness matrix here. I'll follow the convention here. So this is a sample stiffness matrix we have. One. So this is a complete 12 by 12. Okay. But let me check here. There's a figure here from Casimali. So I'm referring to Casimali. That's my main reference here. So as you notice, we have, so if we zoom in here, this is the 12 by 12. So first, the axial. No? We have the axial component. Then this two here will be the bending component. Okay, and also this one is the bending, and this one is the torsion. Okay. So 1, 2, 3, 4, 5, 6. So that corresponds to the 6 displacements. Okay. 1, 2, 3, 4, 5, 6. Something like that. So in short, we should first consider the axial. Okay, that will be the first force, no? Then next will be the, so if you have a cross section like this, so you have the axial first, and then the other two is the F. So if we make the axial is Fx in our case, so this will be Fz, for example, then this is Fy. If this is your Z, local Z axis is over here. Okay, then the rest is the rotation. Okay, so we have a rotation here about this axis, about this axis also, and about this axis. So that will be all in all 6 forces in each node. Okay. Then I implemented that in SMAT. So this is the implementation of that. Okay. So as you notice, in our code, we are required to input the elasticity, Young's modulus elasticity, which is, for example, in this problem, we will solve a steel frame problem, 3D space steel frame. So 205 times 10 raised to 9 because 205 gigapascal. And this is the modulus of rigidity. Okay. This is the inertia about the weak axis. This is the inertia about the strong axis, so IZ. And this is the area of the member for actual consideration. And this is the polar moment of inertia. Okay. And of course, these are the length. So, and those component is required to be able to generate the complete stiffness matrix of this sample member. No? Complete 12 by 12 stiffness matrix. Now, once we generate each stiffness matrix, we're going to find the global stiffness matrix of each member. Take note, this formula here is only for the local axis. No, for this one, for example. Okay. Now, remember, our problem will have this kind of space model. So therefore, we will have a vertical member. Okay, this one, a horizontal member along the x-axis. So if we will draw the global axis of STAAD, something like this, we have x, we have y, a z here, and then y. So the stiffness matrix of this member parallel to the x-axis will be different from the stiffness matrix of this member parallel to the y-axis. And also with this member parallel to the z-axis. Okay, so they're all different, no? Although their local stiffness matrix are the same, because it turns out this is also 5 meters, no? This is also 5 meters, 5 meters. So given that they have the same cross section, no? As you see in this data, they have the same area. They have the same inertia, polar moment of inertia. Okay, because I assumed here a uniform cross section, okay, and a uniform length. So therefore, the stiffness matrix of each member local is the same. Okay. However, when we deal with the global stiffness matrix, they will be different to each other. No, because the formula for the global stiffness matrix is this one, right? It is K global is equal to T transpose K local T, right? Which is still the same with the concept of from the beginning, the truss problem. This is what we follow in order to find the global stiffness matrix. So as you see, it's still the same here in our space problem. It's the same formula. It's just that we have different local stiffness matrix, and then we also have a different transformation matrix as compared to truss problem. Okay. So once we were able to get the global stiffness matrix, by the way, we should, these are the rotational transformation matrix, okay? So for example, as you noticed, the rotational transformation matrix of member 2, so this is my member 2 here. So this is member 1, this is member 2, then this is member 3. Okay, so member 2 is simply a unity matrix. So that means no changes in the local stiffness matrix, right? Because as you notice, its local axis is parallel to the global axis. It's parallel to the local x. The local y is parallel to the global y. And the local z is parallel also to the global z. So see? So in that case, its transformation matrix is unity matrix. Okay. Now it will be different for both member 1 and member 3. So it turns out this is the transformation matrix for member 3, and this is the transformation matrix for member 1 because it's vertical, no? And this R1 sub 3 is parallel to the global Z. Okay. So once you establish that, we can now compute for the global stiffness matrix. Okay. Here, these are the incidences that is required in our formulation of the structure stiffness matrix. Okay. So for example, member 1, its incidence will be, so further understand, I set here as node 1, node 2, node 3, node 4. Therefore, the incidence of member 1 is 1, 2, 3, 4, 5, 6, right? Then 2 is 7, 8, 9, 10, 11, 12. Okay? Member 2, its incidence is 3 to 2, right? This is member 2, right? So its incidence is 3 to 2. So 3 times 6 is 18. So we have 13, 14, 15, 16, 17, 18, right? And its node 2 is 2 times 6 is 12, 7, 8, 9, 10, 11, 12. Okay? And finally, for member 3, its incidence is 2 to 4. So 7, 8, 9, 10, 11, 12. 4 times 6 is 24. So 19, 20, 21, 22, 23, 24. Okay? So consistent, no? So to do that, I have an Excel here to help me with that. No? So in order to automate. So for example, I have more than 3 members. So if I input the nodes here, there's a formula here that automatically computes the degrees of freedom. No? The degrees of freedom per node. Okay. So next is so how many, the global degrees of freedom is 6 times the number of nodes, right? Because we have 4 nodes, so 6 times 4 is 24. So the absolute stiffness matrix of this system is 24 by 24. Okay, because we have 4 nodes times 6 degrees of freedom per node, so we have 24 by 24. Okay. Now, but in that is the absolute stiffness matrix. I call that K sub A. No, but remember, in order to solve this problem, we should have a supports. No, so I have a fixed support here, another fixed support here, right? So in this problem, I made this roller, no, para so that we also have a displacement here and a displacement also on node 3. Now, for the roller, so therefore, how many displacements are we expecting in this problem? So we have displacements on node 2. That will be 6, right? And then how many displacements here? There will be 5, no, because the roller support is only capable to resist the vertical load or the vertical displacement. So 6 minus 1, so that will be 5. So 5 plus 6 here, so therefore 11. So minus 11, so the relative stiffness matrix that we are solving is how many? 24 minus 11 is, yeah, well, it should be 11, no? 6 plus, yeah, so 11. So 11 by 11, sorry. So that's the relative stiffness matrix, no? Meaning relative stiffness matrix because we now consider the number of displacements of our structure. No, the absolute stiffness matrix will not consider the supports. No, now since we already now consider the supports and the displacements, so we have 11 by 11. That's why my code here is 11. Okay, the variable reduced is 11. So meaning the reduced stiffness matrix. We have 3 members, okay, and 4 nodes. Okay, so let's define a null matrix with the size of GDOF, meaning yan yung 24 by 24. So this S4 is the K sub A, no? That one. Okay. So if I run that, so once we know so this code computes the we call this the absolute stiffness matrix. Now, in order to compute the relative stiffness matrix, so I need this data. Where's that? This is my data. This one, no? So remember, we said that we are expecting an 11 by 11. So in this cell, we will input the degrees of freedom that we are solving, no? So remember 7, 8, 9, 10, 11, 12, because this is node 2. 2 times 6 is 12. So 7, 8, 9, 10, 11, 12. Then this is node 3. 3 times 6 is 18, no? Except the vertical. So we were solving from 13 to 18, no? Except 14. Because 14 corresponds to the vertical displacement. Okay, so consistent, right? So this corresponds to 11 unknowns, no? And then these are the 11 degrees of freedom that we are going to solve. Okay, so once you input that, so SMAT will be extracting these values, no? So that's why they are important. So you need to know its addresses, right? So it's it's WX from 25 to 35. So yeah, so 25 to 35. 25 to 35. Okay. And now S5 will be what we call the relative stiffness matrix. No? So once you know the relative stiffness matrix, you can now solve the displacement, right? So from the formula, D is equal to K R inverse P. Yeah, right? That's why I need to define here the P. So these are the loads, no? that we will subject our structure. No? So I have a 100 kilonewton, no, 1000 kilonewton and a 50 kilonewton on the x direction. Okay, so 1 and 2, meaning they are, and ito, 1 and 2. So corresponding to degree of freedom 7 and 8. No. Ito pala, 1 and 2, yeah, 7 and 8. This one. P1, P2, 7, 8. Which is here on node 2. 7, 8, 8 is X and Y, right? So those are the loads, which is this one. Right, so these are the loads, 7 and 8. Okay, siguro I can now erase this. So you know this already. Yeah. Okay, and then okay, once you set up that 12 by 12, so applying the loads, we can now solve the displacement. And actually the displacements are here. Okay, so let me calculate that. Calculate, recalculate. And so these are the displacement. Okay, which corresponds to 7, 8, 9, 10, 11, 12. Okay. So if we will check on our STAAD, yes, okay. So if we will check the displacement here, we have 2.575 going to the left because negative, negative 0.2 going downward, and zero displacement because our load is vertical and going to the left. And if you check on the result for our SMAT, yeah, so we have 2.575, we have 2.47, okay, because this is in meter, no? So 1, 2, 3, that will be 2.47 mm versus 2.575 in Excel, negative 0.2 in STAAD. So the same, no? Negative 0.2 millimeters. And last, 0. So this one is almost 0. Okay? So makes sense, no? Okay. How about node 3? Node 3, remember, corresponds to, these are rotation. So node 3 is this one. So we have 2.47 mm, the same, no? 1, 2, 3, 2.9. Okay, wait. This is X, this is Y. No, this is not Y, no, because this is now Z, no, because remember, we have a restraint on the vertical direction. So 2.9 versus 3.2 millimeters in STAAD. And the rest are rotation. So they're almost the same, no? As compared to STAAD. So we're now able to verify the displacement. Now, how about the forces? No? So to extract the forces, I need another cell here. So remember, we have 12 and 12 displacement per member, right? 6 per each node. No? So this one is corresponding to the degrees of freedom for member. For example, I need to extract the force of the member 3, so which corresponds to N6 to Y6. So have that. Then YZ, then SMAT will extract that for us using this code. Where is YZ? So this is YZ, right? So this is a code to extract the required displacement and member forces. So along with this code, yeah. So this code will combine all the displacements, while this code is the one that extracts the displacement per member. So this is the corresponding displacement of member 3. Yeah, okay. That's why in order to get to forces, K nu sub 3, because remember, it's the global stiffness matrix multiplied by the displacement, no, of the displacement of member 3. And in short, these are the displacements of member 3. Remember, member 3 is this one. We have fixed support here. And there's a 6 displacement here. So 1, 2, 3, 4, 5, 6. And the other end is 0 because we have a restraint. Okay? And then using this formula, this is the corresponding forces. And let's check that. So please ignore this. Okay, let's verify that over here. Maybe I can now clear all the annotation. Okay, so STAAD. So I'll proceed to beam results. Okay, and then member 3, click on member 3. So in short, with that, these are the forces for member 3. So we have an Fx of 2.3, this one, right? Remember, this is member 3. Okay. 17893, so that is 17.9. So this one. So that is, take note, these forces are in local. So therefore, the local axis of member 3 is this one, this is Z, this is Y, and then this is X. So that's why 17.9 is 17.2 here, Fz, because globally, that is parallel to X, right? So this is the global axis, YZ. Okay, so this forces is parallel to the global axis. So this is we call this is along X. Okay, the global X, So 17.9. This is along Y, the global Y. Okay, so 3.93. So Y is 3.9 here. And finally, this is parallel to the global Z, which is Fx in our convention, local stiffness matrix, local axis, I mean. So 2.3 versus 2.3, it's the same, no? And finally, these are the moments. So we have 8.6, 7.7, I think this one. 23.11, STAAD gets 19.5 kilonewton meter. And finally, 10.45, STAAD gets 8.6. Okay? So if we're going to update this, for example, I need to find the forces of member 1. No? So I'll make this 1 here. Okay, and then I'll update this Excel. So I'll make this member 1, which is this one. The address is N4 to Y4. Okay, then Control Shift Enter. Then I'll save this so that SMAT can extract those, and then I'll update this, then calculate, recalculate. So as you see, it also changed. Okay, and this time, so member 1 in our modeling is this one. So as you see, we have 0 displacement on node 1. That's why these are all 0. Okay, so consistent. And finally, for the forces, let us check. Member 1, again, this is consistent to the global X, 332, which is member this one. Yeah. Okay, that's 32. Okay. Then this one is parallel to global Y. So that will be Fx for member 1. So 983. As compared to SMAT, it got 984. Okay. And finally, this is parallel to the global Z here, which is Fy in SMAT, in STAAD, 2.3. 2.3. Yeah, the same. Okay. And the rest are all moments. So 3.9, 3.7, 23.11, and sorry, not 23. This is 90. 90. So this is the 90. 92. 23.11 is 19 only in STAAD. So that's so that's it. Consistent with our SMAT. So that's a sample of 3D space frame problem using SMAT and verified in STAAD. Okay. And by the way, if you wanted to picture the displacement, this is the displacement. And it's consistent because remember we applied a load here and a horizontal load here. So it pushes this member on this direction. Okay.